In this series, we're building up a small 1-bit computer on the breadboard based around the Motorola MC14500, which is a little 1-bit microprocessor. So far, we've built a clock, a program counter, a program storage, and gotten the MC14500 on the breadboard itself with some control for the input. But we don't have any way to take whatever data is showing up on the data bus and put it into an output. So that's what I want to do today. I want to get focused on building the output so we can have kind of a display that outputs a number or something. And there's also one other thing that I want to take a look at, and I want to revamp our Halt setup because I want the MC14500 itself to be able to halt the program if it needs to. So that's what we're going to do today. So let's hop over to the bench, take a look at kind of our game plan, and then we'll pull the breadboard out and put some chips on it, and hopefully it'll all work at the end. So here's our minimal ICU system that we've been kind of following along with so far, and we've got quite a lot built. We've got pretty much all of this built right here. Now the two things that I want to take a look at today are the output and the halt, and they handle the halt a little differently than we are currently handling it. And we're going to take a look at that a little bit later. For right now, I just want to focus on the output down here. And they're using an MC14599. And here's the data sheet for that chip. And so this is essentially just an 8-bit addressable latch. So you have a 3-bit address that comes into the chip here, and that selects which of the 8 bits that you want to store data in, and the data is coming in on the data pin right here. So this is what they mean by addressable latch, is that we can choose the address that we want to store a single bit of data in. And they're actually using it for both the output and the scratch bit. Now, when we come to the scratch bit, we're going to run into some issues because we don't actually have this MC14599. As a matter of fact, I'm actually going to use the 74HC259. This also is an 8-bit addressable latch, but the biggest difference between this one and the MC14599 is that the Motorola version can also put data out onto that data pin, whereas the 74HC259 can only really read from that data output. So that's going to cause some issues when we get to the scratch bit, but that's a problem for future me, so current me isn't going to worry about it at the moment. So let's pull the breadboard out and pop the chip in, and hopefully we can get some output showing up on the LEDs. Okay, so here's our breadboard where we left off last time, and I think I'm going to put the output right over here. So let's go ahead and get that 74HC259 in place. And then we'll do power and ground, which are pins 8 and 16. All right, and then pin 15 here is our reset, and so that's going to run all the way over to this rail here on the far outside. So we'll go ahead and run the jumper for that. Now pin 14 is our chip enable, and this is actually going to be the most confusing pin to take care of because we only want it to be enabled when our write pin is active and when the chip select pin is active. So we need both of those to go high for the chip enable to turn on. Now the chip enable pin is active low, so we need to combine those two signals into one and then invert it. It just so happens that that's exactly what a NAND gate does, so a NAND gate will be perfect for this. So I have a 74HC00 here, which has 4 NAND gates on it, and we'll just go ahead and throw that in the breadboard and get it set up as well. And we'll go ahead and hook up power and ground for it as well. All right, it's a little convoluted because we need to run some jumpers from the right pin over here and the chip select pin here all the way over to that 74HC00 over here, and then we need to run back from the 00 to our 259. But I've got some long jumpers that I think will work, so we'll go ahead and plug those in. All right, that's not the prettiest job I've ever done, but I think that should get the job done. So finished is better than pretty, right? All right, now the next pin on our 259 here is pin 13, and that's the data. So we need to just run a jumper all the way over to the data bus, which is over here. Now, while we're over here on the MC14500, in the previous episode, we didn't actually hook up the reset. We just pulled it low so we wouldn't have any erroneous resets happening. And that's because our reset circuit all the way up here is set up to be active low. So that means that the reset bus over here is pretty much high all the time. And so we need to invert that for the reset pin on here. Well, and it just so happens that we have a 74HC00 here, which if you hook the two inputs of a NAND gate together, that turns them into an inverter. So let's go ahead and hook up our NAND gate here to turn it into an inverter and run that all the way over to our MC14500 so that when we hit the reset button up here, it resets the MC14500 as well. All right, now I think that's pretty much all of the control logic. So next we just need to hook up the address. And the address is going to be pins 1, 2, and 3 here. And they just need to go to these 3 lines right over here. So I've got some jumpers for that, and we'll hook that up right quick. All right, so up to this point, we've got an address coming in, we've got data coming in, and we've got a chip select controls. So we can actually store whatever data is on the data bus in one of the 8 latches that are in here. There's just no way to see them. So let's get some LEDs hooked up in this kind of open spot right here in the middle. So that way we can see the output. All right, now I believe that is everything for the output. But before we go putting power on and start the arduous process of troubleshooting what I hooked up incorrectly, I want to just make my life a little more difficult and go ahead and take care of our Halt setup up here. So let's take a look at what we currently have and then take a look at my game plan for somehow expanding that. All right, so here's what we're using currently to halt the program whenever it's running, is that we have a clock coming in on one input of a NAND gate, and then we have our halt switch coming into the other input of a NAND gate. And so this halt switch must be high for the clock input to actually have any effect on the output. And so when both the clock is high and the halt is high, the output will go low. Now that creates a clock that's inverted of what it actually should be. So we've got another NAND gate here just acting as an inverter, so that we can get the clock passing through as it should whenever the halt is high. And then when we take the halt low, the clock can't pass through. It's pretty simple and it works decently well, but there's no good way for the program to halt itself. And so I want to expand this a little bit. I want to have essentially 3 inputs. I want to keep our halt button just as normal, but I also want to have a flag from the MC14500 be able to halt the program as well. And it just so happens that the instruction 1111 is flag F, and we're not doing anything with this flag, so it would be perfect for using it to halt. And then of course, once the entire thing halts, I want some way to resume it again. So these are going to be our 3 inputs. And so this is the design I've come up with to hopefully make all of this work. So we're kind of borrowing the design from the minimal ICU system in that we're using a set reset flip-flop. And we're creating the set reset flip-flop by essentially just cross-coupling 2 NAND gates. But essentially both the halt and flag F are going into an inverter. And if either one of these goes high, that takes the inverter output low. And the way a NAND gate SR flip-flop works is that both of the inputs coming into it need to be high, and then whichever one pulses low is what causes the flip-flop to set or reset. And so our resume button over here is going to be held high, and then when we push the button, that'll toggle it low, which will reset the flip-flop and allow our clock to continue clocking along. And then these 2 down here are just the same as what we had up here. So all we've done is we've taken this little halt button here and we've made it a lot more complicated. Now I don't have another NAND gate to use as an inverter here, but I have an idea for this, and so we'll pull the breadboard back out and we'll see if we can get all of this to fit into the same space that just this was taking up before. All right, so I've gone ahead and removed all of our old Halt setup from around here so that all that we have left is just the single 74HC00. And actually the only thing still connected up to it is going to be our clock line, which comes in on this one. Other than that, everything's been removed. Now I have quite a lot that I need to stuff in this small area, and I want to start with the resume button. And I'm actually going to put the resume button right where the reset button is. This may sound dangerous in the future, but I think it'll be okay. So I'm actually going to scoot the reset button over 1. All right, and then the output from this resume button needs to go to 1 input of our SR flip-flop. So I'll go ahead and run the jumper for that. And then in order to make our SR flip-flop, we need to cross-couple the output of that NAND gate with the input of another NAND gate. And I'm going to use the NAND gate right on the other side here. So I'm just going to have a little jumper cut across the top of the chip for that. And then the other input of this NAND gate needs to come from the output of this NAND gate. So that's our way of cross-coupling. Now the output of our SR flip-flop needs to act as an input to another NAND gate right alongside the actual clock signal. So we have our clock signal coming in here, so the pin right next to it is going to be the input that we need. But we need the output from this NAND gate on top. But fortunately, that output is crossing over the chip and is available right here. So we're just going to run a small jumper to connect those up. Okay, so now we have the clock being input into a NAND gate as well as our SR flip-flop. And the output of that NAND gate needs to be inverted. So we're just going to use the final NAND gate that's available, which is on this side, and tie the two inputs to that one together, and then run the output of the first NAND gate into the inputs of that one. All right, and then the output of this final NAND gate up here is going to be our clock input to our counter chip over here. So I'll just go ahead and run the jumper for that as well. Okay, that's almost everything, except we're missing two very important things. We're missing the input from our flag F, which is going to be all the way down here by the MC14500. And we're also missing an inverter. So we just need one more inverter, just one single inverter, but there's not enough space on here to fit a full inverter chip. So I need to come up with some solution for this. So I was thinking about it, and all of these chips are just transistors, right? So why can't I just use another single little transistor to get the job done? This may be a little naive thinking, but I figured it was worth a shot. So I've got a little 2N2222 here, which is a little NPN transistor, and I think it can fit in this little bitty space right here in the middle. So we'll go ahead and hook it up as an inverter. And in order to hook it up as an inverter, we're going to hook up the emitter, which is the leftmost pin here, to ground. We're going to hook the collector up to VCC through a 4.7 thousand ohm resistor, and the output will come directly off of the collector here. And then the base will have a little 1000 ohm resistor, and that'll essentially be our control input. Now, when the signal coming into the base is low, the transistor should not be conducting, which means that the 4.7 thousand ohm resistor should pull the collector high. And since our output's coming directly off the collector, that should give us a logic high input into our NAND gate. But if the signal coming into the base goes high, that'll cause the transistor conduct, which should pull the collector down to the same potential as the emitter, which is held at ground, which should have a logic low input coming off of our collector. And speaking of the output and that collector, it goes into just this last input that hasn't been used on this NAND gate right next to here. So we'll go ahead and just run a little jumper for that. All right, so the next thing that we need to hook up is that we need to get flag F, which is all the way down here on the MC14500, up to this base input of our transistor here. That's quite a long journey, and I don't really have any jumpers that are long enough to do that. So I actually took a bit of wire and cut up a custom jumper here. So we'll go ahead and put that in place. That's just about everything hooked up, except that I want to be able to halt this using a button as well. And since we're using an SR flip-flop, we can actually do this with just a push button. But I'm kind of all out of space here, but there's a little bit of open space over here on the right, so I'm just going to put the push button over there. All right, I think that's everything, except for the fact that I now have a bunch more push buttons here, and it could get confusing, so it would be nice if I could color code them a little bit. Fortunately, these push buttons that I got off of Amazon came with color-coded caps. All right, now I believe that is absolutely everything that needs to be hooked up. So let's hook up power and ground and see what happens. Hopefully it'll work. Oh, all right. That's interesting. So the clock was already running and the program counter initialized into whatever random state. We knew that was going to happen. And there's random data stored in our RAM chip here. And it just so happens that we hit 1111, which is our flag F, which it should be our halt signal, which halted it. So even though we have random data on here, we inadvertently tested out the halt functionality. And it actually seems to work. So we're halting it. Let's see if we can resume it. Even though it's random data, let's push this button and just see what happens here. All right, so it resumed just a little bit, but it didn't continue. All right, so it halted again. So I think what I have to be really careful with is that I need to push the button long enough for one full clock cycle to pass. If I'm too quick, it won't clear out the set reset register here. Okay, so our halt is working correctly, but we don't quite yet know if our output is working correctly. We need to put in a program to properly use the output. Now I've come up with a program. It's not short, but I think it'll be a good test of the output here. So I'm not going to subject you guys to watching me program it in real time. So we'll do a quick programming session and then we'll give it a test and see how it goes. All right, I think I've got that all programmed in correctly. It came out to just about 40 steps, so it was a little tedious to program in, but if everything works, hopefully the results should be pretty cool. So right now we're back at program counter 0 here, and you can see that we have absolutely no instructions going on. And the clock is in single step mode. So we'll do the first few steps by hand so we can get an idea of kind of what data is going where and hopefully see if everything's working correctly. So we'll start right here. And so you can see 0110 is our instruction. And this is an OR with the complement. And what that does is it forces a 1 into our result register here. And we want to do that so we can force the input enable register and the output enable register to be active so we can input data and output data. And so the next step should be the beginning of our actual program. And that is 0001, which is a load operation. And we're loading from address 010, which is going to be the number 3 switch down here. And that's set to 0. So we're loading a 0 into the result register. So our input operations are still functioning like they should. So we didn't break anything yet. So that's good. So we'll go to the next step here. And that is a write operation. And we saw our little yellow write LED down here flash while the clock was active. And we're writing whatever is in the result register. So 1000 is a store. And we're writing that into address 000. And one of the interesting quirks that I found out while I was programming this is that my LEDs for my output register here are backwards. The least significant bit is on the far left and the most significant bit is on the far right. So we just wrote a 0 into this bit right here, but because there was already a 0 there, there's no change. All right, so let's step up to the next step here. Okay, and again, we're writing a 0 to address 001. That's the second LED here. And again, it was a 0, so there was no change. Here we go. Now something interesting is happening. So we have a 1001 instruction, and this is a store complement. And so the complement of the result register, which is currently 0, is 1. So we're storing a 1 into address 010. So that's this third LED here. And you can see it came on. So we stored a 1 into the correct address. That worked. That's awesome. All right, so let's do the next step. All right, again, we're storing a 0. So 1000 is storing a 0 into the next address. That's this fourth LED. All right, now we're doing another store complement, and we're doing it into address 1000. So that's this fifth LED here. And then the next step is our halt function, which is instruction 1111, which kicks off our F flag down here, and then that initiates our halt function up here. So right now we're halted, and this is the first number. So it's only 5 bits, but I want to go ahead and write that down. Okay, so we've stored something in there. So what I'm going to do is I'm going to put the clock on run here, and then I'm going to hit this resume button, and we'll see what happens. Okay, it ran through its thing, and we stored a new number, which is 10000. Okay, we'll hit the resume button again. All right, we got yet another number here, 01001. Okay, we'll go resume again. Okay, nothing changed, so that means that we got the same number again, 01001. Okay, and then this should be the last step. Okay, we have a new number, 00011. All right, so we've subsequently stored 5 numbers that are 5 bits each. And this is actually the end of the program. If I resume from here, it's just no operations for the rest of it. So that's pretty awesome. We were able to output something onto our output register, exactly what we wanted. Now, what is it that we wanted? What exactly did I go through the trouble of programming in here to display on our output register 5 bits at a time? 5 bits is a really weird number to work with. Well, we're all familiar with the 8-bit ASCII table, but before that there was something called Baudot code. I think I'm pronouncing that correctly. So this is essentially a 5-bit binary representation of the alphabet that teletypes would send back and forth to each other to send messages back and forth. And the reason I'm using Baudot here is because it's 5 bits as opposed to 8 bits. So that saves me quite a few instructions in the long run. Anything to keep that manual programming down to a minimum. So I've got my little decoder line down here, so we'll go through and decode it one by one here. So we'll start at the top here. It is 00101, and if I look that up, that comes out to the letter H. Okay, and then 10000, look that up, that comes out to the letter E. And then 01001, that's going to be the letter L. And I think you guys can see where this is going because the next letter is the same, so that's also the letter L. And then 00011 is the letter O. So there we go. We wrote our first word. It's not quiet hello world, it's just hello. But our 1-bit computer here was able to output some meaningful data. That is epic. Our 1-bit computer is actually doing something. It's giving us some kind of meaningful output, even if it is very cryptic. But how cool is that? We've got a functioning 1-bit computer sitting on the breadboard. Now we're not quite done. We still have to do the scratch register, which is going to go right here in this bottom corner. But I could not be happier with how the output register is working. The halt segment is still a little finicky. If I push the button too quickly, it doesn't take. Sometimes I got to push the button twice, and then that will oftentimes mess up what shows up in the output register. So I've got to push the button long enough for one full clock cycle to go through and clear out that flag F here. But other than that, this thing is working beautifully. I am super happy with it. And this is turning out to be a really fun, really cool project. So I hope you guys are enjoying following along this hilarious journey of extremely slow computing, because I'm having a blast making this thing. So thank you guys so much for watching, and we'll see you in the next episode.